Chapter 6 Summary. Network Layer. Network applications and services on one devices can communicate with applications and services running on other devices. The protocols of the OSI model network layer specify addressing and process that enable transport layer that data to be packaged and transported. The network layer encapsulated devices to be passed to a destination within a network or another network with minimum overhead. The network layer or OSI layer 3 provides services to allow end devices to exchange data across the network. To accomplish end-to-end transport, the network layer uses four basic processes: addressing end devices, encapsulation, routing, and de-encapsulation. For their addressing and end devices must be configured with a unique IP address for identification on the network. Encapsulation: the network layer encapsulates the protocol data unit from the transport layers into a packet. The encapsulation process adds IP header information, such as the IP addresses of the source and destination host. Routing: the network layer provides services to direct packets to a destination host on another network. To travel to another network, the packet must be processed by a router. The de-encapsulation: when the packet and the services the network layer of the destination host, the host checks the IP header on the packet. If the destination IP address within the header matches its own IP address, the IP header is removed from the packet. After the packet is de-encapsulated by the network layer, the resulting layer 4 PDU layer is passed up to the appropriate services at the transportation layer. The network layer protocols. There are several network layers protocols in existence. However, as shown, there are only two network layers protocols that are commonly implemented. First, the Internet Protocol version 4 and the Internet Protocol version 6. Encapsulating IP. IP encapsulates the transport layer segment or other data by adding an IP header. This header is used to deliver the packet to the destination host. The IP header remains the same from the time the packet leaves the source host until it arrives the destination host. Characteristics of IP. IP was designed as a protocol with low overhead. It provides only the functions that are necessary to deliver a packet from a source to a destination over an interconnected system of networks. The protocol was designed to track and manage the flow of the packets. These functions is required are These functions, if required, are performed by other protocols at the layers, primarily TCP at layer 4. IP connectionless. IP is connectionless, meaning that no dedicated end-to-end connection is created before data is sent. As shown, connectionless communication is conceptually similar to sending letter to someone without notifying the recipient in advance. Connectionless data communications work on the same principle. IP also exchange of control information to establish an end-to-end connection between packets are forwarded. IP also does not require additional fields in the header to maintain an established connection. IP best effort delivery. The unreliable means that IP does not have the capacity to manage and recover from undelivered or corrupt packets. This is because while IP packets are sent with information about the location of delivery, they contain no information that can be processed to inform the sender whether delivery was successful. Packets may arrive at the destination corrupted, out of sequence, or not at all. Provides no capability for packet transmissions if errors occurs. IP media independent. IP operates independently of the media that carry the data at lower layers at protocol stack. IP packets can be communicated as electronic signals over copper cable, as optical signals over fiber, or wirelessly as radio signals. It is the responsibility of the OSI data link layer to take an IP packet and prepare it for transmission over the communication medium. This means that the transport of IP addresses is not limited to any particular medium. There is, however, one major characteristic of the media that the network layer considers: the maximum size of the PDU that each medium can transport. This characteristic is referred to as the maximum transmission unit. Part of the control communication between the data link layer and the network layer is the establishment of a maximum size for the packet. IPv4 packet header consists of fields containing important information about the packet. These fields contain binary numbers which are examined by the layer 3 process. Significant leads in the IPv4 header include the version. It contains a 4-bit binary value set to 0100 that identifies that as an IP version for packet, and the differentiated services of or diffserv or DS, formerly called the type of services field. The DS field is an 8-bit field used to determine the priority of each packet. The six most significant bits of the diffserv field as the differentiated service code point, and the last two bits are the explicit congestion notification. Time to live contains an 8-bit binary value that is used to limit the lifetime of packet. The packet sender sets the initial TTL value and is decreased by 1 each time the packet is processed by a router. The protocol field is used to identify the next level protocol. Limitations of IPv4. Through the years, IPv4 has been updated to address new challenges. However, even with changes, IPv4 still has three major issues: the IP address depletion, the internet routing table expansion, and the lack of end-to-end connectivity. First, IP address depletion. IPv4 has a limited number of unique public IPv4 addresses available. Although there are approximately 4 billion IPv4 addresses, the increasing number of new IP-enabled devices, always-on connections, and the potential growth of less developed regions have increased the need for more addresses. Second is the Internet Routing Table expansion. A routing table is used by routers to make best path determinations. As the number of series connected to the Internet increases, so too does the number of network routes. Lack of end-to-end connectivity. Network addresses translation NAT is a technology commonly implemented within IPv4 networks. NAT provides a way for multiple devices to share a single public IPv4 addresses. However, because the public IPv4 addresses is shared, the IPv4 addresses of an internal network host is hidden. This can be problematic for technologies that require end-to-end connectivity. Introducing IPv6. In the early 1990s, the Internet Engineering Task Force grew concerned about the issues with IPv4 and began to look for a replacement. Improvements that IPv6 provides include increased address space, improved packet handling, and eliminates the need for NAT. Um, in increased address space, IPv6 addresses are based on 128-bit hierarchical addressing as opposed to IPv4 with 32 bits. Improved packet handling. The IPv6 header has been simplified with fewer fields. Eliminates the need for NAT, which with such a large number of public IPv6 addresses, not between a network IPv4 addresses and a public IPv4 is not needed. The 32-bit IPv4 address space provides approximately 4,294,967,296 unique addresses. IPv6 address spaces provides 340 undercillion addresses, which is which is roughly equivalent to every grain of sand on Earth.